What we'll do now is we will work an example problem that enables us to take a look at the idea or demonstrates the concept of exergy. So we have our problem statement, and we're told that we have a thermal energy reservoir. So we have a source, and we're told that it is at 1500 Kelvin, and it's supplying heat flow in the amount of 41.7 kilojoules per second. What they want us to do is to calculate the exergy, or the reversible work potential, assuming the environmental temperature is 25 degrees Celsius, which we had mentioned earlier was the dead state, but we'll just take it as 25 degrees C for now. So what we can do is we can look at this, and first of all, remember exergy is a quantification of the reversible work output. So we need to look at a reversible heat engine in order to determine how much work we can get out of this system. And we studied a reversible heat engine earlier on in the course, and that was the Carnot cycle, the Carnot heat engine. And we have an expression for its thermal efficiency. So let's write that down. So we know for a Carnot heat engine, reversible thermal efficiency can be expressed in this manner. So what we can do is we can substitute in the values of T low and T high. T low is here and T high is here. But what we will need to do for T low is convert it into Kelvin. So I'll have to put in brackets here that needs to be in Kelvin. When we do that and plug that into the first equation, we obtain a thermal efficiency for a reversible process, that of the Carnot cycle, as being about 80%. So now let's draw a schematic of our heat engine. Again, it's a very conceptual one, kind of an abstract one, where we have our source at 1500 Kelvin. Here we have our heat engine, and we have heat flowing in this direction. We were told that the heat flow out of the source is at 41.7 kilowatts. And we will call that Qn. And then all heat engines need to reject to some surrounding environment, and that is the 25 degrees Celsius surrounding temperature. In Kelvin, that is 298 Kelvin. We have reversible work coming out, and we can determine that by taking our thermal efficiency for the reversible heat engine and multiplying by the heat flow in, and that will equal our exergy, which turns out to be 33.4 kilowatts. So to answer this question, we can say that the exergy is 33.4 kilowatts, which is also the reversible work out, because that was the workout that would exist for a Carnot engine, which is a reversible heat engine. And this represents the amount of useful work that is available with this source, assuming that it operates in a reversible manner. So that gives us an example of a calculation involving exergy. It's a very simple one, but it's a good one for us to begin with, and we will do more complex ones as we move along with the idea of exergy and exergy analysis.